In 2021, there was this single struggling microservice that basically caused a cascading network failure and took down half the internet. I mean,
Right.
literally billions of dollars in commerce and communication and logistics just ground to an absolute halt.
Yeah, it was an absolute disaster.
Right. And, if you look at why it happened, it was because a system just kept politely asking a broken, overloaded server for data until every single machine in the chain exhausted its memory and effectively caught fire.
It really was. I mean, it's the absolute definition of a disorganized, chaotic building site where, someone used duct tape and hoped to hold the whole infrastructure together.
Exactly. So today, we're tearing down that disorganized toolbox. We're taking you on a deep dive into the cloud-native API blueprint. Specifically, we've got this whole stack of architectural diagrams and specification checklists, really focusing on Jakarta E and microprofile.
Which is such a fascinating stack to look at right now.
It really is. So the mission for this deep dive is to look at how we build software that actually knows how to survive in the wild. We're going to explore how these open standard specifications interlock to create this cohesive end-to-end factory for API development.
Right, because we have to get away from wrestling with all these disjointed frameworks.
Exactly. We need to actually start building something that won't, take down the internet.
Yeah, and I think it starts by pretty much throwing away the assumption that you can just wing it as you go. Like when you look at the source material for this blueprint, the very first thing it demands is an architect's mindset.
Right. You can't just dive in.
No, not at all. You don't just grab a wrench and start tightening bolts. You have to define the fundamental laws of physics for your system before a single line of code is actually written. And, in the world of APIs, those laws of physics begin with designing the contract.
Contract, right.
Yeah, the blueprint lays out some pretty non-negotiable golden rules right up front.
So let's actually dig into those rules, because I think a lot of developers, and I'm totally including myself here at times, we tend to jump straight into the code. We just want to see something working on the screen.
Oh, for sure. It's human nature.
Right. But you're saying the blueprint forces a hard stop here. So what is the very first law of physics we have to establish?
Well, the absolute foundational law for any cloud-native architecture is statelessness. I mean, it is the absolute prerequisite for scaling.
Statelessness. Okay.
Yeah, it basically dictates that every single HTTP request flowing into your API, it has to contain all the necessary processing information entirely within itself. Like the server is strictly forbidden from holding on to any session state between requests.
So no server-side memory of who I am or, what I was doing 5 minutes ago.
Exactly.
None at all.
I always try to visualize this like ordering food. Like in a legacy stateful system, it's like sitting down at a fancy restaurant, right? You have a dedicated waiter.
That's a great way to think about it. Yeah, and that waiter remembers that you ordered a Diet Coke 10 minutes ago,
Yeah.
and they know you're waiting for a steak, and they know you asked for ketchup. They have this, open session for your specific table right in their head. But statelessness is completely different.
Right. It's totally different. It's the equivalent of a massive high-throughput fast food counter. You don't have a dedicated waiter anymore.
You just walk up to whoever's there.
Exactly. When you walk up to the cashier, you can't just say, oh, hey, I'll take my drink now. The cashier has absolutely no idea who you are or what you ordered previously.
You literally have to hand them a completely self-contained ticket.
Yes, exactly.
The ticket says, I am customer 402, I have already paid for a burger, and in this exact moment, I am requesting a side of fries. And if you come back 3 minutes later to ask for napkins, you have to present that entire context all over again.
That is the perfect visualization. And, the reason this is a golden rule is pure survivability and scale. Like, think about what happens if that dedicated waiter at the fancy restaurant suddenly gets sick and goes home right in the middle of your meal.
Oh man, your order is just gone.
Right, the restaurant is thrown into total chaos trying to reconstruct your state. And in a cloud environment, servers go down constantly. I mean, they're completely ephemeral.
They just pop in and out of existence.
Exactly. So if an API relies on a specific server instance, remembering a user session, and that instance crashes, the user is abruptly logged out and their data is just lost.
Which is a terrible user experience.
It's the worst. But with a stateless fast food counter, any cashier can process any ticket at any given time. If one cashier goes on break or, one server instance is destroyed by Kubernetes, the load balancer just routes the next incoming ticket to a different cashier. The user experience is absolutely zero disruption.
Okay, that makes total sense. You're basically sacrificing the convenience of the server remembering you in exchange for infinite resilient scalability.
Yeah, that's exactly the trade-off.
So that's the first rule. But the source material outlines a second golden rule for this blueprint, and it comes with this massive acronym, HATEOAS, hypermedia as the engine of application state.
Yes, HATEOAS.
Let's break that down because, I mean, come on, it sounds like something straight out of a theoretical computer science thesis.
I know, right? It sounds incredibly academic. But the actual mechanics of it are beautifully practical. The core idea is that your API responses should include hypermedia links to related resources. It basically introduces dynamic API discovery.
Okay, but how does that actually work in practice? Like, if I make a request to get some user information, what am I actually getting back from the server that makes it dynamic?
Okay, so think about a standard non-HATEOAS API. You might ask for user ID 123, and the server just sends back a basic JSON payload with a name, an email, and an account balance. And that's it.
Just the raw data.
Right. Now, if the client application wants to update that user's email or check their recent orders, the developer who wrote the client application had to go read your static documentation and physically hard-code the URLs for those subsequent actions right into their source code.
Oh, right. They literally have to type out, like, api.mycompany.com, Easers123 orders directly in their front-end code.
Exactly. And that's super brittle. But with HATEOAS, the server's response payload includes the name, the email, the balance, and then an additional section, which is usually an array of links.
Oh, interesting.
Yeah, and these links explicitly tell the client, hey, here's the exact URL to update the email, here's the URL to view recent orders, and here's the URL to close the account.
It's essentially providing a map along with the data.
Precisely.
You know, this feels incredibly similar to how humans actually use the internet. Like, when I go to an e-commerce website, I haven't memorized the exact URL path for the checkout page or the customer service portal.
But you don't type it from memory.
No, I just go to the homepage, I read the screen, and I click the hyperlinks the server provides to me in that specific moment. I navigate the state of the application dynamically.
That is exactly the mechanism. HATEOAS does for machines what websites do for humans. And the architectural benefit of that is massive decoupling.
Because the front end isn't guessing anymore.
Exactly. If the front-end client is dynamically reading the links provided in the response rather than relying on hard-coded strings, the back-end API is suddenly totally free to change its internal routing structure.
Oh, wow.
Yeah. Like, if you want to move the orders endpoint to a completely different microservice with a brand new URL path, you can do it without breaking the front end at all.
Because the backend just updates the URL it returns in that hypermedia link array.
Exactly. The client doesn't care what the actual URL string is. It just blindly follows the link labeled view orders.
That really changes the paradigm completely. You aren't just serving data anymore. You are serving the state machine itself. The client is basically just a dumb terminal following instructions.
It really is.
I can definitely see why that's a golden rule for long-term survival. You don't end up with, you know, thousands of legacy mobile apps crashing just because you tweaked a URL path.
Exactly. It saves so many headaches down the road.
Okay, so moving on to the third rule in the blueprint, resource-based naming. The sources say we should be using plural nouns for collections, like users, and we should express relationships hierarchically, like department's 5 employees.
Yeah, the critical concept to grasp here is that URLs must be nouns, not verbs. A URL is an identifier, right? It identifies a thing on your server. A user, a department, a document.
Right.
It should never describe the action you actually want to perform on that thing.
Which brings us directly to the things that will make the building inspector shut down your site. The anti-patterns. The sources emphatically state that we must avoid verb-based actions.
Absolutely.
So instead of a URL like get user.id1, it should just be users1.
Yes, because the HTTP protocol already has verbs built into it. Get, post, put, delete. Embedding verbs into the URL path is like saying ATM machine. I mean, it's redundant, and it completely breaks the standardized contract of the web.
Yeah, I'm completely on board with avoiding verbs and URLs. That makes total sense. But the sources list a second major anti-pattern, and I really have to push back on this one.
Okay, let's hear it.
They call out deep nesting as an architectural sin. They say you should avoid paths that are deeper than 2 levels. And the example they give to avoid is something like users 1 orders items 3.
Right.
Now, hold on. If I have a highly complex relational database, deep nesting feels completely natural to me. It perfectly models reality. A user possesses an order, and an order contains items. So why is it an anti-pattern to go 3 or 4 levels deep if the data is literally structured that way in my system?
I get why it feels natural, but here's the issue. An API should never, ever be a mirror of your database schema. It needs to be a facade.
A facade.
Yeah. When you expose a deeply nested path, like users 1 orders 5 items 3, you're essentially forcing the outside world to understand and rely upon your internal data hierarchy.
Oh. So I'm exposing the structural blueprints of my database to every single client application that calls me.
You are tightly coupling them to it. Let's look at the business reality of software evolution. What happens 2 years from now when the logistics department decides that items shouldn't strictly belong to a single order anymore?
That happens all the time.
Right. What if items are now trapped independently as part of a global fulfillment batch that spans multiple users? If your API is nested 4 levels deep based on the old logic, you're trapped. You cannot refactor your database without breaking every single client application that relies on that massive, brittle URL string.
Because the client is basically passing in a breadcrumb trail that no longer exists in my database.
Precisely. By keeping paths shallow, for instance, just jumping straight to items 3, you decouple the API's surface area from the underlying data model. If an item has a unique ID, you don't actually need to know the user ID and the order ID just to fetch it.
That's true.
Shallow nesting creates flexible, bounded contexts. It allows your internal data structures to evolve rapidly without constantly breaking the public contract.
Okay, I see it now. It's kind of like hardwiring a lamp directly into the wall's electrical grid behind the drywall instead of just using a standard outlet.
That is a great way to put it.
Yeah, because the moment you decide to rearrange the living room and move the lamp, you have to tear down the entire wall. Shallow nesting provides those standard outlets. You just plug the client in where it's needed.
That is the essence of the design phase right there. We've established the rules, be stateless, use hypermedia, name things as nouns, and keep the hierarchy shallow.
Okay, so we have the blueprint for the contract. We know what to call things and how to structure the requests. But how do we actually execute actions? How do we build the machinery that receives these nouns and, actually does something with them?
Well, this is where we operationalize those HTTP methods we mentioned earlier. The blueprint establishes a really strict, standardized mapping between the HTTP verb the client uses and the action the server performs.
So this is how we get that predictability.
Exactly. If a client wants to create a brand new resource, say a new user, they strictly must use the POS key method.
And the sources are very specific about the expected server response for a P-post. It shouldn't just be a generic OK. It needs to return a 201 created status code.
And crucially, that 201 created response must include a location header.
A location header.
Right. When you create something, the server has to tell you where it actually put it. The location header provides the exact URI of the newly minted resource, so the client immediately knows how to find it later.
So the client says, POS users with a JSON payload of my name. The server processes it, saves it, and replies, 201 created. And by the way, here is your receipt. You can find this specific data at users 99 from now on.
Exactly.
Yeah.
That's the flow. Then we have the JCEditor method. This is exclusively for reading or querying data. It is fundamentally an idempotent operation, meaning you can call it 1,000,000 times and it will never, ever change the state of the server.
Right.
It should return a 200 OK with the requested data, or a 404 not found if the resource identifier simply doesn't exist.
Idempotency is such a crucial concept to highlight here for you listening. Just the idea that doing the same thing twice shouldn't cause a disaster. Which brings us to put and delete.
Right, so put T is used for a full update or replacement of an existing resource. If you send a PT request to users 99, you are replacing the entire representation of that user with the new payload you provided.
Got it.
And that should return a 200 point. And delete is, well, self-explanatory. It removes the resource. A successful delete usually returns a 204 no content, which basically signals the action was performed, but there's no payload to send back to you.
Now, there is a drafting note in the source material regarding get to requests that I found really interesting. It explicitly states that query parameters, the things you see at the end of a URL like .limit150 or sort ascending, those strictly must be used for metadata.
Yes.
They should never be used to initiate an action.
Because query parameters are adjectives, not verbs. They modify how the noun is presented to you. They filter, they sort, they paginate. You should never, ever design an endpoint like users.action delete an ID 99.
That just feels wrong to even say out loud.
It does. It completely violates the semantic contract of the web. The HTTP verb itself is supposed to be the action.
Okay, so we have the strict theory of HTTP verbs and status codes. But, theory only goes so far. What does it actually look like for a developer sitting at a keyboard trying to build this?
Right, getting to the code.
Yeah, the source material provides a visual of a Jakarta REST resource class. And the overarching theme that jumps out is just total decoupling.
Decoupling is the primary driver of developer productivity in this entire blueprint. Historically, writing a web server meant writing mountains of procedural code just to parse raw TCP/IP byte streams, extract the HTTP headers, figure out what the URL even was, and then manually convert text into variables.
Which is just
It
exhausting.
is exhausting, error-prone plumbing.
But when you look at the Jakarta REST code, it's just pristine Java. There is no plumbing visible anywhere. Instead, the entire routing mechanism is handled declaratively through annotations.
Exactly. You have a standard Java class, and right above it you drop an @pathUsers annotation.
Hmm.
That single line of text tells the framework's internal reflection engine to map all incoming traffic for that URL hierarchy directly to this specific class.
It's so clean.
Yes. And inside the class, you have a method called createUser, and you drop an @post annotation right above it. You've instantly mapped the HTTP verb to the business logic.
I think of these annotations kind of like highly specialized bouncers at an incredibly exclusive nightclub. Like the actual Java method, the code, calculating the business logic, checking inventory, finalizing the transaction. That's the bartender deep inside the club, quietly making the drinks.
That's brilliant. And in the old days, that bartender had to do absolutely everything.
Exactly. Before these declarative blueprints, the bartender had to stop mixing drinks, run all the way to the front door, check everyone's ID, search them for contraband, figure out if they were speaking English or Spanish, and then run back to make the drink.
It was a terrible use of a highly skilled worker.
Right. But with Jakarta REST, you put the bouncers at the door. And honestly, the most ruthless bouncer of all is Jakarta Bean validation.
Oh, absolutely. The validation engine is a brilliant example of failing fast before the business logic is ever even touched.
Right. In the code, next to the incoming data parameter, there are these annotations like @valid and @notnull and @email. This triggers a massive verification process before the Java method is even invoked.
It catches so much garbage.
Yes. The client sends a JSON payload. If they forget to include a required username field or they provide a malformed email address, the @valid bouncer immediately throws them out of the club. It intercepts the request and instantly returns a 400 bad request status code along with a detailed error message.
And the bartender never even knows it happened.
Exactly. Your business logic is never even interrupted.
Think about the cognitive load that removes from the developer. You don't have to write 50 ICE statements at the top of every single method, checking if a string is empty or if an integer is negative. The framework guarantees that if a request actually reaches your method body, the data is pristine and perfectly matches your required constraints.
You just write the logic that actually matters to the business.
Precisely.
It is incredibly elegant. But there is a missing link here that we need to talk about. The HTTP request arrived at the door speaking JSON. It's just a giant string of text characters, but our application speaks Java.
Right. It deals with structured objects sitting in memory heaps.
Exactly. So how do they actually communicate? How does the string of text become a usable object in memory before it gets to the bartender?
That requires a translation layer. In the Jakarta E blueprint, this is called the serialization engine, and it's primarily handled by message body readers and writers. It bridges the gap between the wire protocol and the application memory.
Okay, let's trace the inbound path first. The client sends the JSON string over the network. It hits the bouncer. What happens next?
So the framework intercepts the raw text stream and routes it to a message body reader. The default implementation in this blueprint uses JSON-B, the Jakarta JSON binding API.
Okay.
The reader essentially acts as a deserializer. It parses the JSON text, identifies the keys and values, dynamically instantiates a new Java object in memory, let's call it a create user request object, and populates its internal fields with the exact data from the JSON string. And only then is it handed to the validation engine and your business logic.
And the outbound path is just the exact reverse of that mechanism, right?
Exactly.
The bartender finishes making the drink. The business logic completes its calculation and creates a user response Java object in memory. The framework grabs that object, hands it to a message body writer, which inspects all the fields, translates them back into a correctly formatted JSON text string, and ships it out over the wire as the HTTP response body.
Right. And while JSON is obviously the undisputed king of modern APIs, the blueprint is intentionally designed for extensibility. The source notes that developers aren't permanently locked into JSON-B.
Which is good to know.
Yeah, if you are integrating with some legacy banking system that strictly requires XML or maybe a modern configuration engine that speaks YAML, You don't have to tear the framework apart.
You just swap it out.
Pretty much. You can write a custom translation class by implementing the reader and writer interfaces and simply tag it with the @provider annotation. The framework will automatically discover your custom translator at startup and add it to the content negotiation engine.
So if a request comes in with an HTTP header saying content type application YAML, the framework automatically routes it to your custom YAML reader instead of the standard JSON reader. That's total flexibility.
Yeah, and without changing a single line of your actual business logic.
All right, so the data has successfully breached our perimeter. It was validated, translated from JSON into a Java object, and our business logic calculated a result. Now, we actually have to save it. We need to bridge the API to the database.
This is the tricky part.
It is, and this is where the sources introduced something that made me raise an eyebrow. Jakarta Data 1.0. The blueprint describes it as a way to unify data access using a declarative repository pattern engine.
This represents a massive, massive evolutionary leap from traditional database connectivity. Historically, if a developer wanted to save an object to a database, they had to write awful JDBC code or complex JPA-Java persistence API criteria queries. You had to manually open a database connection pool, write raw SQL strings, map the resulting database columns back to Java variables, manage transaction boundaries, and write these massive finally blocks to ensure the connections were closed so you didn't crash the whole database.
It was an absolute nightmare of boilerplate plumbing. But the source slide for Jakarta Data explicitly claims, zero implementation code required. Runtime generates the bridge dynamically.
I know exactly what you're going to say.
Well, as a developer, whenever a framework promises me zero implementation code, my internal alarm bells just start ringing. Because usually that translates to, we are hiding a mountain of terrifying complexity behind a magic curtain, and when it inevitably breaks in production, you will have absolutely no idea how to debug it.
It's totally fair.
I mean, is this actually magic, or is it a trap?
That skepticism is entirely warranted. Every experienced architect fears unexplainable magic. But we have to make a really vital distinction here between implicit magic and explicit abstraction.
Okay, tell me the difference.
Magic is when a framework does things behind your back based on obscure, undocumented naming conventions. Jakarta Data is not magic. It is an explicit compiler-level abstraction.
Okay, I'm listening. Walk me through the mechanics of it. How can I possibly query the database without actually writing the query?
You start by writing a standard Java interface.
Yeah.
You annotate that interface with @repository. Inside that interface, you declare a method signature. For example, you write listUserFindByRegion, string region, and you annotate that method with @find.
And that's it. I just write the signature. I don't open curly braces and write the actual logic inside.
You don't write the method body at all. When the application compiles or starts up, the Jakarta Data Engine reads that explicit interface contract. It uses an abstract syntax tree analyzer to parse the method name. It sees find, it sees by, it sees region.
Okay.
Because it understands the shape of your user object, it dynamically generates the highly optimized implementation code right in memory to execute that query against your target data store.
Wait, so it's effectively writing all the boilerplate for me on the fly.
Exactly. And the real power of the repository pattern is that it abstracts the underlying database technology. Whether you are connected to a traditional relational PostgreSQL database or a NoSQL document store like MongoDB, the Jakarta data provider generates the correct dialect, either SQL or a NoSQL query language, to fulfill the exact contract you defined in the interface.
The aha moment for me here is really the elimination of human error.
Yeah.
Like if I write 50 SQL queries by hand, there is a very high probability I'm going to introduce a SQL injection vulnerability in at least one of them, or I'm going to forget to close a connection and cause a memory leak.
It happens to the best of us.
It really does. But if the compiler engine is generating the data access code based on a mathematical understanding of the AST, it generates perfectly parameterized, secure, resource-safe queries every single time.
It standardizes the data access patterns across your entire engineering organization. You basically stop reviewing pull requests for malformed SQL strings, and you start reviewing them for actual business value.
I buy it. It's not magic. It's just delegating the tedious, highly structured plumbing to a machine that's frankly way better at it than I am.
Exactly.
All right, let's take a breath. We have designed the API blueprint. We've built the REST implementation using bouncer annotations. We've translated the JSON. We've saved the data to the database using the zero-code repository engine. The internal machinery is complete.
But we aren't done yet.
No, because an API is effectively useless if no one in the outside world knows how to use it, or if it is just a miserable experience for client developers to integrate with. That brings us to living documentation and consumption.
Documentation is famously the most neglected phase of the software engineering lifecycle. In traditional shops, an API is built, and then some junior developer is tasked with writing a static wiki page describing how it works.
Which is the worst job.
It is. And the fatal flaw is that the second the code base is updated with a new parameter or a changed status code,
Yeah.
that wiki page becomes dangerously outdated. It literally becomes a source of lies.
And there is nothing more frustrating than spending 3 hours debugging an integration, only to realize the API documentation was just wrong the whole time.
It's infuriating.
The cloud-native blueprint attacks this problem by demanding that documentation is not an afterthought. It must be a living contract. And it achieves this using the microprofile OpenAPI specification.
Right, and it uses the exact same philosophy we just saw with routing and database access.
Yeah.
Declarative annotations sitting directly on the source code.
Okay, so right above my bartender logic, alongside the @POST and @path annotations, I add documentation annotations. I drop an @operation annotation to provide a human-readable summary, like registers a new premium user.
Yep.
And I drop an @API response annotation to explicitly state that if they get a 400 status code, it means invalid email format. I'm literally writing the documentation directly into the Java file.
Which means the documentation is tightly bound to the implementation.
Yeah.
When a developer modifies the code to add a new required field, the documentation annotations are right there staring them in the face, practically prompting an update.
You can't ignore them.
No, you can't.
Yeah.
Furthermore, during the build process, when your CI/CD pipeline compiles the application microprofile, OpenAPI acts as this automated gear system. It churns through every single class in your project, reads all those annotations, and dynamically generates a raw, machine-readable JSON or YAML schema file that perfectly describes the entire API surface.
Oh, nice.
Yeah, and this schema is typically exposed automatically at the OpenAPI endpoint.
But I mean, a raw JSON schema file isn't exactly fun for a human to read.
No, but it is absolutely perfect for machines.
Yeah.
And that leads to the second half of the engine. The framework simultaneously feeds that machine-readable schema into an interactive web interface, usually Swagger UI, which is hosted at OpenAPI.
This is where static text transforms into a living testing ground. Developers don't just get a boring wall of text to read, they get a beautiful interactive web page.
Exactly.
They can see the exact JSON structure the API expects. And honestly, the best part is the try it out button. They can type a dummy payload directly into the documentation UI, hit execute, and the browser sends a real HTTP request to the API, displaying the live response right there on the page. It completely eliminates the friction of initial integration testing.
It creates a self-documenting system that guarantees the documentation is never, ever out of sync with the deployed code. But providing a beautiful instruction manual is only half of the consumption equation.
Right.
The other half is how client applications actually write their own code to talk to your API. And the source material highlights a fascinating architectural fork in the road right here. They outline an API consumption strategy showdown between two fundamentally different approaches.
The client showdown. I really want to unpack this because choosing the right client really defines how painful your day-to-day development will be.
It really does.
So on one side, we have the Jakarta REST client. The blueprint describes this approach as programmatic and imperative. It utilizes a client builder and a web target mechanism.
So the imperative approach means you are explicitly telling the computer how to do every single step. You instantiate a client object. You define the target URL as a string. You manually append query parameters one by one. You construct the HTTP request object, and then you execute it.
The pros are pretty obvious. Maximum flexibility. Like if you are dealing with a chaotic legacy third-party API where the URLs are highly dynamic and unpredictable, or you need to manually manipulate raw HTTP header bytes, the programmatic client lets you get your hands dirty.
Yeah, use total control.
But the cons. It is incredibly verbose. You are writing a lot of repetitive boilerplate code, and you are entirely responsible for manually managing the memory lifecycle of that client object so it doesn't just leak connections.
Now contrast that with the challenge on the other side of the ring,
Okay.
the microprofile REST client. This approach is declarative and type-safe. It uses a completely different mechanism. Instead of writing procedural steps, you define a Java interface that perfectly mirrors the API you want to call. And you just drop a @register as client annotation on that interface.
You essentially write a blueprint of the remote server.
Exactly. And the pros are immense. It dramatically reduces boilerplate code.
Yeah.
But the absolute killer feature is its native integration with CDI context and dependency injection.
Let's define CDI for you listeners who might not be deep into Java enterprise frameworks. Dependency injection is a pattern where, instead of a developer using the new keyword to create an object in memory and managing its lifespan, the framework handles it.
Right.
You just use an @inject annotation, and the framework says, oh, you need a client to talk to the billing service. Here is a fully constructed, memory-managed client ready to use.
And that's exactly what happens with the microprofile REST client. You just type it inject at REST client billing service, and you can instantly call Java methods on that interface. The framework intercepts the method call, translates it into an HTTP request, fires it over the network, parses the JSON response, and hands you back a clean Java object.
I have an analogy for this showdown that I think clarifies the trade-offs perfectly.
Well, let's hear it.
Choosing between these two clients is exactly like choosing between driving a car with a manual transmission and an automatic transmission.
Okay, let's explore that. How does the manual transmission map to the Jakarta client?
Well, the Jakarta REST client is a manual stick shift. You have your hand on the gear selector, your foot constantly working the clutch. You are doing significantly more physical work. It's verbose.
Yeah.
But you have ultimate granular control over every single RPM and gear change. If you are navigating an incredibly complex, unpredictable, chaotic off-road course, which is exactly what integrating with poorly designed dynamic legacy APIs feels like, you want that manual control. You need to be able to ride the clutch.
I agree completely. And the microprofile client.
That's the modern automatic transmission. You just put it in drive, press the gas pedal, and steer. The @registrS client and CEI mechanisms handle all the complex gear shifting, clutch timing, and RPM matching under the hood. It's smooth, it's standardized, and it drastically reduces your mental workload. Most of the time, when you are just driving down a newly paved highway, meaning you are communicating with a well-documented, predictable internal microservice, you absolutely want the automatic transmission.
It's an excellent analogy because, honestly, neither tool is objectively wrong. They are just suited for different environments.
Yeah.
If your architecture involves internal microservices communicating with each other where the contracts are stable, the microprofile client keeps your codebase incredibly clean and type-safe.
Yep.
But if you are building an aggregation engine that needs to dynamically spider across the web, scraping unpredictable ad hoc endpoints from 100 different third-party vendors, the rigid interface of the microprofile client will absolutely break down. You will need the imperative flexibility of the Jakarta client.
The blueprint basically gives you both tools. The architect's job is to choose the right one for the terrain.
Right.
Right. So our API is built, it's documented. Other services are successfully consuming it using their automatic transmissions. We are in production. The API is out in the wild.
The scary part.
Yeah, this is where the theoretical blueprints hit the brutal reality of physics. Real users are hitting the system simultaneously. Real networks are dropping packets. Real database servers are experiencing CPU spikes. How do we keep the system alive when the environment turns hostile? This brings us to the operations phase. The training wheels come off.
When you migrate from a single monolithic application running on one server to a distributed cloud-native architecture spanning dozens of containers, the fundamental nature of failure changes completely. In a monolith, if a method fails, you get a stack trace in your log file.
Simple enough.
Right. But in a distributed architecture, you aren't just worrying about logic errors in your own code. You are dealing with the inherent unreliability of the network connecting 10 different independent microservices. The source material addresses this reality by introducing the Cloud Native Operations Dashboard, which is constructed on 4 distinct pillars.
So let's identify the problems and the solutions for each of these 4 pillars. Pillar 1 is resilience. The core problem is network failures and the terrifying threat of cascade crashing across services. And the blueprint solution is the microprofile fault tolerance API.
Correct.
Pillar 2 is security. The problem is that traditional stateful sessions, like our fancy restaurant waiter trying to remember everyone's order, just don't scale across distributed server clusters. The solution is stateless perimeter security using microprofile JWT.
Exactly.
Pillar 3 is observability. The problem is that a single user request gets lost inside a distributed black box just bouncing between a dozen services. When it's slow, you have no idea who's to blame. The solution is microprofile telemetry for distributed tracing.
Yes.
And finally, pillar 4 is orchestration. Your cloud environment, like Kubernetes, is totally blind. It needs to know when to kill a container that is locked up or when to route traffic to a newly initialized pod. The solution is microprofile health, utilizing standardized health live and health ready endpoints.
Those 4 pillars literally form the operational bedrock. Let's do a deep dive into that first pillar, resilience. We need to understand the anatomy of a cascading failure. Because in a distributed system, network failure is not just a possibility, it is a statistical certainty.
Right. Let's paint a picture of that disaster. So we have Service A, the front-end gateway, and it needs to call Service B, the inventory database, to complete an order.
Exactly. Now, imagine Service B experiences a sudden CPU spike and starts responding very slowly. The network calls from Service A begin to timeout. What happens inside Service A? Every incoming user request requires a thread from the service thread pool to process it. If Service A makes a network call to Service B, that thread sits there completely blocked, waiting for a response.
It's just twiddling its thumbs, doing nothing but consuming memory.
Right. And because Service B is slow, those threads in Service A are piling up. Within seconds, Service A has exhausted its entire thread pool waiting on Service B. Now, Service A can't process any requests, even ones that don't need inventory data at all. Service A crashes. And if Service C relies on Service A, Service C crashes next. That is a cascading failure. To prevent this, the blueprint provides the circuit breaker pattern.
The circuit breaker. I immediately visualize the electrical panel in my garage. It operates on the exact same principle. If my toaster shorts out, the breaker instantly flips and violently shuts off the electrical power to that specific circuit in the kitchen.
Yes, exactly.
It does that to isolate the failure so the wires don't overheat, melt the insulation, and burn the entire house down. It sacrifices the kitchen to save the structure.
And the microprofile fault tolerance API maps directly to that mechanical concept using a highly sophisticated state machine with 3 distinct states. The first is the closed state.
Which feels a little bit counterintuitive to non-electricians because closed sounds bad, like a closed road. But in electrical engineering, a closed circuit means the drawbridge is down.
Exactly. The circuit is closed, meaning the connection is complete. Electricity, or in our case, network traffic, is flowing freely from the client to the target service. Everything is operating normally.
But then the chaos hits. The target service starts struggling. The database locks up. Network packets are dropping. The error rate begins to spike.
The Circuit Breaker API is constantly monitoring the error rate and the timeout rate of those outgoing calls. When that failure rate crosses a predefined threshold, say 50% of requests fail over a rolling 10-second window, the circuit breaker violently trips. It moves into the open state.
Okay.
The target service is now officially suspected of failure. And here's the critical survival mechanism.
Yeah.
It fails fast.
What does failing fast actually mean for the code, practically speaking?
It means the framework intercepts any new attempts to call the broken service. It doesn't even try to open a network socket. It doesn't wait for a timeout. The moment the code attempts to make the call, the framework instantly throws a circuit breaker open exception back to the calling method.
Which psychologically feels really wrong to a lot of developers. Our instinct is to be persistent. We want to wrap it in a while loop and retry over and over until we get the data. Why is giving up instantly and failing fast considered a good thing?
Because endless retries create the thundering herd problem. If the target service is struggling because it is overwhelmed by traffic, hammering it with thousands of automated retry requests is the absolute worst thing you can do. You are basically guaranteeing its death.
Oh, that makes sense.
By failing fast, the circuit breaker acts as a crucial pressure relief valve. It cuts off the traffic, giving the struggling service vital time to catch its breath, clear its backlog, and recover.
And more importantly, it saves the calling service. By failing fast, the thread in service A isn't blocked waiting for a 30-second timeout. It gets the exception instantly, it handles the error, and that thread is immediately released back into the pool to handle other users.
Yes.
It stops the cascade crash dead in its tracks. It is so much better to return a quick, graceful service, temporarily unavailable message to one specific user than to hang the entire system and crash your front-end servers for everyone.
It is defensive driving for distributed architecture. But the software breaker has a massive advantage over the mechanical breaker in your garage. When your kitchen breaker trips, you have to physically walk to the garage in the dark and flip it back on. How does the software breaker know when it's safe to resume traffic?
This brings us to the third state, which is brilliant, the half-open state. After a configurable waiting period in the open state, maybe 30 seconds, the circuit breaker doesn't just blindly throw the floodgates back open. That could instantly crush the recovering service again. Instead, it cautiously transitions to half-open.
This is a probationary period recovery testing.
Right. It allows just a tiny trickle of traffic through.
Right.
Maybe it lets one or two test requests slip past the barrier to ping the target service. I love visualizing this. It's like the breaker nervously flipping itself back on, sending a tiny pulse of electricity to see if the toaster is still sparking, or if I finally had the sense to unplug it.
If those test requests in the half-open state execute successfully without errors or timeouts, the breaker realizes the crisis is over. The target service is healed. The breaker snaps back to the closed state, the drawbridge lowers, and full traffic flow resumes automatically.
And if they fail?
If those test requests fail, the breaker instantly realizes the service is still down. It snaps back to the open state and starts the 30-second waiting period all over again.
And the most beautiful part of this entire complex state machine, a developer implements it just by adding a single @circuit breaker annotation above their REST client method. They don't write the timing loops, the state tracking, or the error threshold math. The framework handles the heavy lifting of resilience.
It's incredible.
Okay, moving on to the observability pillar. We've stopped the failures with circuit breakers, but with dozens of microservices talking to each other asynchronously, how do we actually see what's happening? When a user clicks checkout and the request jumps through the gateway, the cart service, the inventory service, the payment gateway, and the shipping ledger, and it takes 10 seconds, how do you find the bottleneck? Do you just grep through 50 different server logs trying to match timestamps?
That is the nightmare scenario of distributed debugging, and it's exactly why the source material highlights illuminating the black box using distributed tracing, specifically microprofile telemetry, which is built directly on the industry-standard OpenTelemetry specification.
So it provides a way to trace the path of the electricity through the entire grid. The blueprint breaks this down into two fundamental identifiers. The first is the trace ID.
The trace ID is the unifying thread. The moment a user's HTTP request hits the very first ingress point of your architecture, the API gateway, the telemetry engine generates a unique, globally consistent identifier. It's this massive randomized alphanumeric string. Think of it as a cryptographic passport for that specific user's journey.
And that passport gets stamped onto the HTTP headers. As the request jumps from service A to service B to service C, every single microservice is required to read that trace ID from the incoming header, include it in their own log messages, and pass it along in the header to the next service downstream.
Exactly. When you open your observability dashboard like Jaeger or Zipkin, you just paste in that trace ID, and the system instantly pulls together every single log line from every single server that was involved in that specific user's request. It connects disparate, chaotic logs into a single cohesive narrative.
But a narrative isn't enough when you are debugging performance. Knowing the journey doesn't tell you who is actually slow. That's where the second identifier comes in, the span ID.
Right. While the trace ID tracks the entire end-to-end journey, a span ID measures the execution time within a specific localized boundary. Service A has its own span ID, and a stopwatch starts the moment it receives the request and stops the moment it finishes its work. When it calls Service B, a new span ID is generated for Service B's workload.
And what's really powerful is that developers can get incredibly granular with these spans. The blueprint shows the @with span annotation. If you have a specific method deep inside your Java code, maybe a complex pricing algorithm or a database query that you suspect is unoptimized, you don't have to guess. You drop @with span directly on that specific method.
And the telemetry engine will automatically intercept that method call, start a high-precision stopwatch, execute the method stop the watch, and attach that specific microduration to the overarching trace ID.
So when you look at your dashboard, you aren't just seeing a vague warning that the payment service took 4 seconds. You see a beautiful waterfall chart that says, the gateway took 10 milliseconds, the payment service took 4 seconds, and exactly 3.9 of those seconds were spent executing the calculate tax method on line 42. It provides pinpoint, surgical accuracy for debugging latency.
It totally replaces guesswork with empirical data. So we can observe the traffic flowing through the system and we can stop cascading failures. But how do we ensure the entities generating that traffic are actually who they claim to be? This brings us to the security pillar. Stateless perimeter security using microprofile, JWT.
JWT JSON Web Token. This is where we bring our very first golden rule statelessness full circle. Let's contrast this with how security used to work. In a traditional, stateful system, when a user logs in, the server generates a random string of characters called a session ID. It hands that ID to the browser as a cookie, and it saves that exact same ID into a central database, along with the user's details and permissions.
Right. And every subsequent time that user makes an API request, they send that session ID cookie. The API gateway receives the ID, pauses everything, makes a network call to the central database or a Redis cache, looks up the ID, and asks, is this session still valid, and does this user have the admin role?
And in a massive cloud environment, processing tens of thousands of requests per second, forcing your gateway to make a database lookup for every single API call is a catastrophic bottleneck. The database will literally melt.
Which is why the blueprint mandates JWTs. A JSON Web Token completely flips the paradigm. Instead of handing the client an empty reference ID, the authentication server packs all the user's information, their user ID, their email, their expiration time, and crucially, their roles, like teller or admin, directly into a JSON payload.
But wait, if you're just handing the client a JSON object with their roles in it, couldn't a malicious user just open the token in a text editor, change their role from user to admin, and send it back to the server to hack the system?
They could alter the text, but the server would instantly reject it. And this is the magic of the cryptographic mechanism. Before the authentication server hands the JWT to the client, it mathematically hashes the header and the payload, and it signs that hash using a highly secure, heavily guarded private key.
Okay, let's break down the cryptography. The private key is a secret mathematical formula that never, ever leaves the authentication server vault.
Correct. The resulting cryptographic signature is appended to the end of the JWT. Now, the API gateway, the bouncer at the front of our cluster, doesn't have the private key, but it does have the corresponding public key. The public key can't create signatures, but it can mathematically prove whether a signature was generated by the true private key.
So a user sends the JWT in their authorization header. The gateway intercepts it. It takes the payload, runs it through the public key algorithm, and compares the result to the signature attached to the token. If a hacker altered the word user to admin, the payload has changed. The math will no longer match the signature. The public key verification will fail, and the gateway will immediately throw a 401 unauthorized error.
Exactly. The gateway verifies the identity and the permissions purely through mathematics. The slide explicitly states the benefit: zero database lookup required. Because the cryptographic signature proves the data within the token is authentic and untampered, the gateway doesn't need to ask the database. It just trusts the token.
And because of this complete architectural decoupling, the Java resource method, our bartender, remains blissfully stateless. The developer doesn't write complex security parsing logic. They just put an annotation like @rolls_allowed teller directly above their business logic.
Yep.
The microprofile framework automatically extracts the roles from the validated JWT claims and enforces the perimeter. If the token says user and the method requires teller, the bouncer blocks the request.
It is an incredibly elegant, infinitely scalable security model.
It is elegant for scaling, yes, but I have to push back hard here. We really need to talk about the dark side of stateless tokens.
Okay, let's hear it.
If there's truly zero database lookup, if the gateway is purely doing math to verify a signature, how on earth do we handle revocation? What if an employee goes rogue and is fired at 2:00 p.m.? What if a user's laptop is stolen at a coffee shop and their JWT is compromised?
Right.
In the old stateful system, the admin just deletes the session from the database. The next time the stolen cookie is used, the gateway checks the database, sees it's gone, and blocks them. But with the JWT, the gateway isn't checking a database, it's just doing math. Won't the gateway mathematically verify the stolen token and let the hacker walk right through the front door until the token naturally expires? Isn't this a massive, unacceptable security risk?
You are hitting on the exact nerve of the stateless architectural compromise. It is the classic trade-off. You are trading absolute instant revocation capability for infinite bottleneck-free scalability. Because the token is mathematically self-contained, you cannot intrinsically revoke it without breaking the fundamental rule of statelessness.
So what is the actual engineering solution? Because we can't just accept the hackers get a free pass for hours.
The primary mitigation strategy relies on extremely short expiration times. You do not issue JWTs that live for days. You issue JWTs that are valid for like 15 minutes.
But forcing a user to log in with their password every 15 minutes is terrible UX.
Which is why the client application handles it invisibly. The authentication server issues the 15-minute JWT, but it also issues a long-lived stateful refresh token. The refresh token is saved securely in the database. When the 15-minute JWT is about to expire, the client application secretly sends the refresh token to the server to request a new JWT.
Ah, so the refresh token process is stateful.
Exactly. If an employee is fired, the admin revokes the refresh token in the central database. The fired employee's current JWT will technically still work, but only for a maximum of 14 minutes and 59 seconds. Once it expires, their client tries to use the refresh token, the server says revoked, and they are permanently locked out.
Okay, but For high-security applications, banking, healthcare, military logistics, even a 15-minute window of vulnerability is completely unacceptable. If someone steals a token, 15 minutes is plenty of time to drain an account.
If the domain demands instant revocation, architects are forced to compromise the pure statelessness by introducing a denialist or blacklist cache at the gateway.
Wait, a deny list? If the gateway has to check a list of revoked tokens for every single incoming request, haven't we just completely reintroduced the exact stateful database lookup we were trying to kill with rule number 1? How is that any different than a session ID?
It is entirely different based on the order of magnitude and computational complexity. Let's look at the math. In a stateful system with 1 million active users, the gateway has to execute an ON database lookup against a table of 1 million active sessions for every single request.
Yeah.
It has to constantly ask, is this one of the million good ones?
Right, which causes the bottleneck.
But the denialist, the gateway is only checking the bad ones. How many tokens are actively revoked and unexpired at any given millisecond? Maybe 50? 100? The gateway doesn't query a disk-based database. It holds an O1 in-memory hash map containing just those 50 revoked token signatures.
Oh, I see.
When a request comes in, the gateway does the cryptographic math and then does an instantaneous nanosecond check against the tiny hash map in RAM. It asks, is this one of the 50 bad ones?
Okay, I see the nuance there. You are technically reintroducing state, but you are doing it at such a microscopic, highly optimized scale that it doesn't incur the architectural penalty of a full database lookup. Architecture truly is never perfect. It's just a continuous series of well-reasoned, heavily debated compromises based on the laws of physics.
Exactly. You balance the need for scale against the domain's tolerance for risk.
We have covered an immense amount of ground today. We started with the foundational blueprint rules. We built the REST implementation using declarative bouncers. We tackled JSON translation. We abstracted the database with the zero-code repository pattern. We generated living documentation. We chose our client transmission. We protected against cascading failure with circuit breakers. We illuminated the black box with distributed tracing. And we secured the perimeter with cryptographic mathematics. It is. Now, I want to pull all of these disparate threads together. We need to see the synthesis. Let's watch a single HTTP request travel through this entire cloud-native ecosystem we've just constructed.
This is where the true elegance of the blueprint proves its value. Let's walk through the anatomy of a cloud-native request, layer by layer, exactly as the source material synthesizes it. Step 1. The HTTP request arrives at the ingress point of the Kubernetes cluster.
Step 2. The security layer. The API gateway intercepts the request. It extracts the bearer header. It mathematically validates the cryptographic signature of the JWT using the public key, performing zero database lookups unless checking a tiny deny list. The microprofile framework evaluates the @roles_allowed annotation to ensure the user actually has the correct permissions to enter the specific endpoint.
Step 3. The observability layer. The moment it passes the security checkpoint, microprofile telemetry kicks in. It reads the incoming header, generates or propagates the unique trace ID, creates a new span ID for this specific service, and begins ticking the high-precision stopwatch to measure execution time.
Step 4. The resilience layer. Before the business logic is even allowed to execute, the microprofile fault tolerance engine inspects the @circuit breaker annotation. It evaluates the current health of the target system. Is the error rate below the threshold? Is the circuit closed? If the path is clear, it permits the execution to proceed.
Step 5. The interface layer. The request finally reaches the Jakarta REST boundaries. The URL path is matched via the @path annotation. The HTTP verb is mapped via @post. The JSON-B serialization engine wakes up, parsing the raw incoming JSON text stream, checking constraints with @valid, and seamlessly deserializing the text into a fully instantiated, perfectly valid Java object sitting in memory.
Step 6. The persistence layer. The core business logic, the bartender, finally does its work. It calculates the tax, applies the discount, updates the ledger. It then hands the processed object off to the Jakarta data at repository interface. The dynamically generated AST compiler code translates the intent into an optimized, injection-proof SQL query and saves the data securely into the backend relational database.
And finally, Step 7. Egress. The entire process runs in reverse. The newly saved entity is returned as a Java object. The message body writer serializes it back into a JSON string. The framework applies a 201 created HTTP status code, automatically generates the correct location header URI, and sends the response back down the wire to the client. Simultaneously, telemetry stops the stopwatch and asynchronously logs the final execution span to the tracing dashboard.
It is beautiful. It is exactly like watching a perfectly orchestrated, high-tech assembly line in an advanced manufacturing plant. The user's data flows rapidly down the conveyor belt, and at every single station, a highly specialized robotic arm swings down.
I love that image.
Yeah, those robotic arms are our declarative annotations. At rolls allowed, at circuit breaker, at valid, at POST, at find. Each arm performs exactly one specific, highly complex task flawlessly and instantly passes the data to the next station. The data flows through the entire factory without ever missing a beat, and the developer didn't have to write the mechanical control code for a single one of those robotic arms. They just pointed to the blueprint and said, put a circuit breaker here.
And that visualization perfectly encapsulates the concluding insight of the source material, the open standard advantage. The true power of this platform is not the individual capabilities of tracing or routing. It is how seamlessly these independent specifications layer over one another via standard annotations to create a unified whole.
Right. Why does this specific blueprint matter for the long haul? The slide uses the phrase stability meets agility. Jakarta EE and MicroProfile represent an open consensus. They bridge the gap between established, rock-solid enterprise reliability and modern, lightweight, container-optimized cloud architecture.
The business value of that open consensus cannot be overstated. By programming your application against abstract specifications rather than proprietary vendor implementations, you're protecting your organization's most valuable, expensive asset, its code base.
Let's talk about vendor lock-in, because that is the nightmare scenario for an architect. If I write my application tightly coupled to a specific cloud provider's proprietary routing library or a proprietary vendor-specific security SDK, I am trapped. I am effectively married to them. If they decide to double their licensing fees next year, or worse, if they deprecate the tool entirely, I have to rip open my application and rewrite core business logic just to keep the lights on.
Exactly, you lose all your leverage. But with the open standard advantage, your code relies exclusively on the abstract blueprint. You just write a circuit breaker or add POST. You don't care which underlying software library actually executes the circuit breaking logic or parses the HTTP bytes.
It's an interface contract.
Precisely. Your code base remains portable. You can pick up your entire API factory and deploy it on a local open source server for testing. You can move it to a heavy-duty enterprise application server. Or you can compile it down to a native binary using Grail VM and deploy it straight into a Kubernetes cluster using lightweight runtimes. The deployment environment changes, the underlying implementation libraries change, but your source code, the core intellectual property of your business, does not change a single character. It is standardized, it is resilient, and it is insulated against whatever chaotic evolution the tech industry brings next.
So we've journeyed all the way from a disorganized, chaotic building site relying on duct tape and hope to a cohesive, beautifully layered, cloud-native factory blueprint. We've seen how the strict rules of statelessness and noun-based resource naming set an unshakable foundation. How Jakarta REST and JSON-B radically decouple the HTTP transport from the business logic. How Jakarta Data eliminates SQL plumbing by dynamically bridging the storage. How OpenAPI transforms static wikis into living, interactive contracts. And how MicroProfile wraps the entire structure in a shield of resilience, observability, and cryptographic security.
It represents a profound, necessary shift in how we engineer software for the modern era. It moves developers away from writing fragile infrastructure plumbing, allowing them to focus entirely on writing pure business value.
And as we wrap up, I want to leave you, the listener, with a final provocative thought to mull over. If we have truly reached an architectural inflection point where our infrastructure blueprint handles all the heavy lifting, if the framework handles the complex routing, if it mathematically verifies the security tokens, if it generates the living documentation, if it automatically trips the circuit breakers when networks fail, if it tracks the latency of every method, and if it even dynamically generates the database queries for us, what does the future of a developer actually look like? Are we rapidly moving toward a world where the act of coding is no longer about writing procedural logic, but simply becoming an architect who understands how to orchestrate the right declarative annotations in the exact right order? Thank you for joining us on this deep dive into the blueprint. I highly encourage you to open up your own code bases tomorrow morning, take a hard look at your architecture, and honestly ask yourself, where are you still using a disjointed toolbox when you could be utilizing the factory blueprint?